meaning like the pack extra credit and the web assigned extra credit, meaning like if you did the requirements, you'll get it. Okay, so let us proceed. All right. So last time we talked about, sorry, hold on. We talked about dimension, what it means to be, what it means for a vector space to have dimension, right? Hold on. Let me just pull this up so it could be easy for me. Because I need to see you in the chat. So hold on. Okay, that's true. This is fine. Okay, so hold on. Let's see if there's any more chats that are. Okay, perfect. Oops. Okay, so last time we talked about dimensions. So now what I want to talk about is a few more things about dimensions and how to find dimensions of a vector of subspaces and stuff like that. So I think the last thing we did was show some dimensions of some subspaces, right? Or some, I guess, some vector spaces. So it stands to reason that a subspace would also have a dimension, right? So that we've talked about dimension of a vector space last time. Now the question is, do subspaces have dimension? And the answer is yes. Again, it is determined by the number of basis elements, right? So again, remember, as soon as you know what the spaces is for a space, count the number of basis elements, meaning just count however many it took to like span the entire space. That would be the dimension of it. Okay. So okay. So let's look at some examples on how to do this. So let's look at something like this. So what was the last example we talked about? This one. So example 4.54. Find the dimension of each subspace. Okay. And the first one we're going to look at is subspace. I guess it's a subspace of R3 with the standard operations. So the first one we're going to do is this one. The space where the set of all such points looks like this. So it's D, C minus D, and C. such that C and D are in R real numbers, okay? And this is obviously a subset of R3. Okay, so how do we check if this is a subspace? So remember, a subspace, what the basis for this is. So remember, what does it mean to be a basis, right? Well, a basis is, again, it just satisfies two requirements. It spans the entire space, and each one of them are linearly independent, right? But we could also say that it's the least number of vectors that we need in order to write every other vector in that space as a linear combination, right? So look at this right here. So for this one, let's look at this. So okay, let's pick an element in here. And again, by the way, so this it should be more like D, C minus D, and C. So it's a vector in R3, right? So observe that we have D, C minus D, C. And again, so just pick this inside my W. We can write this as D minus D 0. Or maybe it'd be easier for you to see this. So I'm gonna split this vector up. So basically 0 C C minus or maybe do plus D minus D and 0, right? So do you see how I just split up this part right here? I just split it up to two vectors. But now look at this. So now let me factor out a C from the first one. Oops, should be 1, 1. Plus D, which would be 1 minus 1 and 0. Do you see? You can see from here that that every vector in W can be written as a linear combination of the vectors 0, 1, 1 and 1, negative 1, 0, right? Okay, so that means that these two vectors span W, right? But not only do they span it, also these are linearly independent, which means that this is the basis for W. Okay, so again, what's the key point here? The key point is that, remember what a basis is. A basis is like the atoms of the space you're in. Everything that's in that space can be made out of like combinations of those basis elements. In this case, 0, 1, 1 and 1, negative 1, 0. So these are a basis for W. Okay? So since they're a basis for W, that means that the dimension of W has to be determined by the number of these. So in this case, it's 2, right? So since I guess we call the basis V, the basis 0, 1, 1 and 1, negative 1, 0 has 2 elements. The dimension of W in this case is 2. Okay, so remember, that's all you have to do is once you find the basis, you find the dimension. Okay. What about the second part? So what about W is a set of all vectors that look like 2b, b, and 0, such that b is a real number. Well, again, do the same thing we did in the first one. Take an element. Observe that for 2b, b, and 0, what I can rewrite this as b, 2, 1, and 0, right? Since every vector since every vector can be written as a linear combination of 2, 1, 0, this is a basis for W. Okay, so the dimension of W in this case is going to equal 1. Okay, so this was a one-dimensional subspace. So see how in this one, even though this vector has 3 components, right? I mean, it's part of R3. It's a subset of R3, right? It doesn't mean it's going to be 3-dimensional. It's a 1-dimensional. The other one as well, right? That one was 2 dimensions. So just because you take a subset of a vector space, let's say R4, and you know that the dimension of the vector space is 4 in that case, doesn't mean those subsets will have the same dimension. What you can be guaranteed of is now this. So I guess you can say remark. A subspace will never exceed the dimension of a vector so they will never exceed the dimension of a vector space, or not of its, I guess you can say, parent vector space. Okay, it could be smaller, it could be the same, but can never be larger than the actual spaces you're taking it from. Okay, so hold on, let me see if there's any. Okay, yeah, I can go back for a second. Okay, so again, so this is how you can find this if you're given an explicit like these examples, right? These examples gave you the exact form of what these vectors look like, right? So I give you an explicit picture of what the vectors in this look like. But what if now I give you something like well, this thing is now I just give you 3 vectors and I give you the span of it. What about in that case? But so hold on. Okay, so let's ask this question now. So, question: Can any subset of a vector space, let's say V plus times, have a dimension? Oops. And what do you guys think the answer to this is? Okay, if I take any subset of a vector space, can that thing have a dimension? So, what do you guys think? Yes, that is correct. So can it equal the parent? Yeah, for sure. I mean, if you I guess if you were to take a subset that contained all the basis elements, what I mean, the dimension will never exceed the bigger subspace, right? I guess your question is, can so the dimension could equal the parent's dimension, but never exceed it. Yeah, correct. And yes, the answer is actually, sorry, what was the question? Yeah, so the question was, can any subset of a vector space have dimension? And the answer is actually no, it can't. So here's the reason why. The answer is no. Because you need a structure of a vector space on it. So only subspaces can have dimension. Okay, so remember, so let me go back here. So remember, remember how we said when we take a subset of a vector space, that doesn't mean it's a subspace, right? Well, the reason that I was like telling you to check if this is a subspace, because that thing that you're getting, a subset of the vector space, won't always be a subspace. And if it's not a subspace, then you can't talk about having dimension. It has to have a subspace. It has to have a vector space structure on it in order for it to have a base, to have a dimension. So you can talk about dimension. So yes, I was just seeing if if anybody was gonna ask a question. Maybe this is kind of inconvenient that I can't. So hold on, let me just. Hopefully I can maybe do it on here. So let me see. Yeah, perfect. Yeah, don't want that. Hold on. Okay, can everybody hear me fine? Okay, perfect. I was just trying to pull the chat up on my phone, but okay. So okay, so again, so a subset has dimension. Not every subset of a vector space is a subspace. So not every subset will have dimension. So the reason I'm bringing this up is because a subset. So yeah, subspaces will have dimension, but a subset will only a subset of a vector space. So say I take this subset, I don't know, like, so here's R3, right? So here's the entire vector space, and let's say I just pick out the vector 1, 1. The set that contains 1, 1 is a subset of it, right? However, it doesn't have a dimension because it's not a subspace. So this is not a subspace. No, and so therefore it has no dimension. Okay. So the only way a subset will have a dimension is if it's a subspace, and you check that using the subspace test, right? The theorem I gave out. But yeah, so why am I even talking about this? Well, because remember there was a theorem we talked about that the span of some vectors is actually a subspace. So the span is a subspace, and therefore you can talk about it having dimension. So here, recall that the span of, say, a set of vectors is a subspace. Okay, so the question is now, if, so let me see, let's say W is equal to span of U1, UN, what is I guess you say, the dimension of W? Well, the answer is this. The number, or linearly independent vectors in this net set. Okay. So let us now talk about the example that goes along with this. Okay, so find the dimension of W equals span of S where S equals -1, 2, 5, 0, 3, 0, 1, -2, -5, 4, 9, 2. Okay. So literally, according to the answer to this question I posed, you just have to find out which one of these, well, how many of these are linearly independent. So if you remember that we have already talked about this, all you have to do is take these vectors, put them in in augmented form, or just in a matrix, RREF it, and then find the ones that have pivot positions, right? And I'll show you what that means right now. So look at this. So putting S in matrix form, like this, right? So then let me get my calculator out and put this in my calculator. -1, 2, 0. Sorry, hold on. 2, 0, 4, 5, 9, 0, -2, and 2. So if I RREF this is what I get. I get 1, 0, 2. So you see here, we only have two pivot positions, right? So this one corresponds to this one, and this one corresponds to this one. So only two are linearly independent. Which is those two, right? The red one and the blue one. So this is a basis for that. So that means that the dimension, which implies that the dimension of W is equal to 2. Okay? So that's all you literally have to do is see how many of these vectors are linearly independent if you're given it as a span, and that'll be the dimension of that subspace. Okay. Okay, so any questions on this? Okay, all right, so let's move on to the next theorem and then finish off the section. So let's check this. So theorem. So actually, let me see, have I given this theorem already? Yeah, I don't think that. So that was 4.52. Okay, so this one I'm gonna state it and then tell you how its usefulness. No, you don't have to show the steps for RREF. As long as you just give me the RREF of the matrix and just tell me how many pivot columns you have or linearly independent vectors you have, that'd be more than fine. Yeah, so now from now on, you don't have to show the steps for RREF. You just use your calculator and that's it. All right, so the V be a vector space with dimension n. So this one, what it pretty much says is this. So remember how I always told you that you have to check that the basis or the set of vectors spans the vector space and that it's linearly independent to check it as a basis? Well, you no longer have to do that. What this theorem says is that you just have to check one of them, and that's enough. So, one, if this set S is linearly independent, set in V, then S is a basis for V. And then two, if S, again, as you go to this, spans V, then S is a basis for V. So what this is telling you is that you don't have to check both conditions. For a finite dimensional vector space. Okay. One is fine enough. So that's what we basically did in this one, right? We just showed you, all I showed was which, in this one I found that two of them were linear independent. So that means that these two are basis for that subspace span S. So you only ever have to check which one is linearly independent, and that's it, or whichever spans the space. You never have to check both anymore. And this is only for finite dimensions, right? Okay. So any questions so far? Okay, perfect. Okay, so now that we've talked about all this abstract stuff, the next thing that we can talk about is how does this relate to what we are using it for, like solving systems of equations, right? Yeah, sure. Which page? This one? So when we talk about solving systems of equations, we talked about when we have unique solutions, no solutions, and infinite solutions, right? And then we've also talked about when something has a solution and when it doesn't. Oh, sorry, unique solution and when it doesn't, right? And we talked about the determinant, and that determinant helped us determine whether a system has a unique solution or not, right? We talked about, like, we had it in a matrix form. It has a unique solution if and only if the determinant is non-zero, right? Well, that was, like, in a sense, like using determinants to help us find if this thing has solutions. Now we can go even further. We can now use these structures that we've learned about vector spaces, basis, spanning, and all this other stuff to be able to determine whether something has solutions or not, and also the behavior of the solutions and how they can even look like, right? So let us move on to section 4.6. Section 4.6, which is the rank of a matrix and systems of linear equations. So the rank is so I've mentioned it already, like briefly, like maybe in chapter 1 or 2, I like informally defined it. But now that we know what dimension is and basis is and all that stuff, we can now define it like precisely. Okay. So consider a system of equations, say like a11 times x 1 all the way to, let's say, a1n xn equals b1 all the way to an like this, right? And then this can be written as a equals a11 a1n an1 all the way an n, and this should be n. Or vector x, it's going to be x1 to xn, and b is b1 to bn. Okay, so this is, and then you can write it in this form, right? Ax equals b. Okay, so we have these forms. I just want to remind you all, like, what where all this like connects, right? So all of these are equivalent, right? Okay. So now we can talk about something called row space and the column space of a system of equations. And since they have the names space, arrow, you mean these arrows? Oh, those are, that just means that if and only if, but like how like how someone said it's the same mass, yeah. These all three of these are the same mass, yeah. So we can now look at some vector space structures on systems of equations. Definition. So let A be a n by n matrix with real entries. We have 1, the row space of A is a subspace of Rm spanned by the rows of A. Okay, so literally just take the rows of A. So like say this is A, right? So let's say we have A, and here's my rows, R1. And then you can also write it in columns. C1. Oh, I think C1 is better with notation. A1. AN. You can write it this way. But so the row space is literally just this. So the row space is equal to the span of R1 to Rn. That's literally all what it is. And then the column space is literally just the space spanned by the columns. So the column space is the subspace spanned by the columns of A. So row, sorry, span of A1 to AN is the column space for this matrix. And they all have a subspace structure, which means you have dimension, right? Okay, so it's 2 minutes till. I'll probably end it right there. But any questions, comments, or concerns? Sure. Is this page or which one? For sure. I will try my best to get those today. For sure. Like I'm almost done with them. Like literally, like super, like close to finishing. Okay. Any other questions? Nope. Okay. Well, then I'll see you guys. About a week, I'd say we would have. So about the same time. Yes. So I'll give a review, and I'll basically change up the the. I'll keep the type of questions the same, but change up the questions. The questions like how we did last time, but the format will be the same. I think it was like April like 11th or something like that. But I'm gonna give a few more days because this last test I had to give a few days later. It's in the syllabus. I can resend the syllabus to everyone for you guys to see. I can actually update it to the actual to a more accurate test date for test 2. Yes. Here. Okay. Any other questions? Let me actually send you guys this because I keep forgetting.